So hopefully all of you remember this question. It is a little bit longer, so it's maybe difficult to, I mean, it will be time consuming to read this whole thing, but basically what we have is a one-channel, two-rank system, right? One-channel, two-ranks DRAM system, and each channel has its own memory controller. We have 8 banks, and you were asking about the timing diagram. Which part is that exactly? So let's see what it says here in the question. DRAM is refreshed every 64 milliseconds, running by command from the memory, which occupies command bus on the associated memory channel and the associated bank. Okay, so a single refresh command will only refresh a single bank from that rank, right? So that means you can, every 5 nanoseconds, the memory controller is free to issue different refresh command to different bank, or the same bank if it's ready, if it's completed the previous refresh operation, right? So to answer your question, every 5 nanoseconds, the memory, you can expect the memory controller to put a refresh operation to any available bank in any of the ranks available on the system. So so let's say this is time 0, and time goes this way. So if, for example, here until 5, you have a refresh to, let's consider only a single rank, one rank, right? So you refresh, let's say, bank 0, rank 0, bank 0. After 5 nanoseconds, you can also put here another refresh command to refresh bank 1 or any other bank. So you can pipeline those, right? But here, at this point, you cannot refresh bank 0 again because bank 0 is already being utilized. It is already being refreshed. So we should wait 40 nanoseconds. Right. To issue a refresh to the same bank, you need to wait at least 40 nanoseconds. So this is a little tricky, actually. I think it is. So it is tricky, but I believe it is clearly defined here because in C here it says what data bus utilization across all memory channels is directly caused by DRAM refreshes, right? So what you say is kind of an indirect result because DRAM is being refreshed and basically you cannot access this bank, so you cannot read anything out of it. You cannot utilize the data bus. That's true, but it is not directly because of refresh, because the refresh command itself is not using the data bus. Yeah. You only give the address, the bank address, to the DRAM. The memory controller only gives the bank address, and the data bus idle otherwise. So if you have another rank, for example, this data bus can be utilized by the other rank if it's not under refresh. So you can't say that the refresh operation is utilizing the data bus, actually. It may cause the data bus to be underutilized, but it is kind of a side effect. It's not a direct effect. Yeah.
When we issue a refresh command to a certain bank,
so it depends on what kind of refresh command you're issuing. So in DDR3, DDR4, in real implementations, there are bank level and rank level refresh commands. So if you issue a rank level refresh command, all the banks in a rank are being refreshed. So yeah, so the entire rank is unavailable. But if you issue per bank refresh, which is available with DDR4, I guess it's not available in DDR3, then you can access other banks. Yeah. So here in the question, it clearly says that associated memory channel for 5 milliseconds and the associated bank, right? So this means this is a bank level refresh command. Okay, the next question is from the second homework. This is question 5 from homework 2. Okay, so it covers caching and processing in memory. And the question is like this. So it defines two integer arrays, A and B, and they have elements of size 4 bytes. And here you can see the base addresses of A and the base address of B. And here we have a piece of assembly code. So I won't go through this code now, but instead I will directly jump to the question. I think it will be easier if you do so too, because first trying to understand the code might be more difficult if you don't know what to answer. Okay, it makes more sense to first read the question. So here it further says that we have a single core processor that executes this code, and this processor does not have any caches. The load store instructions access directly the main memory, and then we have a fixed latency of 50 cycles for both read and write operations, and those are serialized. So it's pretty easy so far, right? Everything is serial. We have fixed latency, no cache, and memory requests cannot be overlapped. Okay, so everything is pretty straightforward, and then the execution time of non-memory access instructions is 0. So here in this code, we will take into account only memory accesses. Okay, and then the question is, what's the execution time of this piece of code on this processor without any caches and 50 cycle main memory latency? So now if we look at the code, we see that we have two loops named outer loop and inner loop. And if you check here, what is the condition for the branching against the inner loop? It is basically this, this case where R4, register 4 is not equal to 2. So here we set R4 to 0 at the beginning of the outer loop, and here we increment it, right? Anywhere else in the code, we don't modify R4. So basically, this will mean the inner loop will execute once. At the end of the first iteration, we will increment R4, and here we will compare 1 against 2. And since 1 is not equal to 2, we will need to repeat the inner loop one more time and then exit. Okay, so the inner loop will execute 2 times. And then the outer loop will execute how many times? So here it will branch on R3 equals 16. And then we increment R3 here, and we set R3 at the beginning of the program. So this basically means the outer loop will iterate 16 times. And in each outer loop iteration, we will do the inner loop twice. Okay, in total, we have 32 inner loop iterations. Okay, so inside the inner loop, we have 2 loads. Let me use a different color here. So we have 2 loads. And at the end of the outer loop, we have a store here. Since we execute this twice, the inner loop twice, we'll have 2 loads. 2 loads per iteration and 4 loads per outer loop iteration, and then followed by 1 store. And then we will repeat those 5 memory accesses 16 times. Okay, and then the answer of this first part is pretty easy, right? So we have 16 outer loop iterations. We do 5 accesses, and each access takes 50 nanoseconds. And then if you do the math here, it's basically, sorry, this is cycles, not nanoseconds. And the answer will be 4,000 cycles. Okay, this part is pretty easy, right? Any questions on this? Okay, so now it becomes a bit more complicated because we add a 128-byte private cache. And here are the properties of this cache. So the cache block size is 8 bytes. Okay, so based on this information, we can directly see that we can fit 2 elements, right, into one cache block. This is important. And then the cache is direct mapped. And access to the cache takes 5 cycles. And on a miss, we go to the main memory and then again pay the 50 cycle latency. And the question is the same. So if you have this cache, what will be the execution time of this code here? Okay, so this part is a bit more tricky. First, we need to understand exactly where in this cache elements of A and B will map. So we know that the cache is direct mapped, and it has 128-byte capacity in total, and each cache block is 8 bytes. So basically, here we'll have 16 entries that are direct mapped, right? So I find it basically by dividing 128 by 8. So it will look something like this. So this is the first set or entry, and then second and third, and we have this until 15, right? So then if we look at the base addresses here to determine where in this cache the first elements of A and B will map, so we can first basically find out which bits of the address tells us the entry in the cache to access, right? And then since we have 128 bytes here, the last 8 bits of the address will have to do something with the cache, right? So basically, since we have 8-byte blocks, the last 3 bits of the address will be the offset, right? So which byte within the cache block is addressed. So like those 3 bits, least significant 3 bits will indicate that. And then, this is 4. And then the next 4 bits here of the address will tell us which entry of the cache that address is targeting. So if we convert this hex number to binary, we will see that we have like a bunch of zeros here. So we'll have 12 zeros, and then here we'll have 1. Right, so we can easily see that here the first element of address A will go to the first entry of the cache because all least significant 7 bits are 0. And so it's the same for B, for the base address B. Again, here we have 12 zeros, right? So this basically tells us that the first elements of A and B will conflict on the first cache line, on the first entry over here. So basically, when we access A0, when we want to access A0, it will bring A0 and A1 to this position. And then if we want to access B0, it will evict A0 and then put B0 and B1. Okay? So based on this, we can now start understanding what this access pattern looks like. So here in this code, we see that R1 is the base address of A, and then R2 is base address of B. So this first load is targeting some element of A, and then the second one is targeting an element of B. So here we use R5 to iterate over this array, and here we use R4. So R5 is calculated by adding R3 and R4. So we already have some understanding about R3 and R4. R4 is basically the counter that we modify inside the inner loop, right? So it gets either 0 or 1 as a value. And then R3 is the outer loop iterator, which gets values from 0 up to 15. And so basically what will happen here is we will first access A0, right? Because initially R5 will be 0 plus 0. And then in the next iteration of the inner loop, we'll access A1. And for B, we'll access B0, and then B1. So those will be the locations we will touch in the first 2 iterations of the inner loop. And then here, for the store, it is R1 plus R3. And R3 is our outer loop iterator. So it will be basically the base address of A plus R3, which initially will be A0. Okay, and in the next iteration, what will happen is we first, after we complete the first outer loop iteration, we will go back here, we will reset R4 to 0, and then we will calculate R5 as 1, because we incremented the outer loop iterator, plus 0, so we'll have 1 here, and then we'll access A1 first, and then we'll access A2. Okay, but for B, nothing changed. We'll again access the first element of B, B0, and then B1. Is that clear? So basically it goes like this. A0, or let me put it that way. So we touch 0, element 0 of A, and then 1, and then 1 again, and then 2, and then 2 and 3. It goes this way. But for B, we basically repeatedly access elements 1 and 0 and 1. Okay, so here it's not only important to determine exactly which locations we access, but also the order of those accesses is important because they are conflicting in the cache. So in addition to compulsory misses that we'll have, we'll also have conflict misses in the cache, right? And let me show that too. Okay, so in the first outer loop iteration, those will be the addresses that we will access, right? So we will first access A0, and then we'll access B0, and then A1, and then B1. And then finally, we will do A0 again to store the value that we calculate. So initially, the cache is empty. We'll get a cache miss. So this is a compulsory miss for A0, and then same for B0. This is the first time we access B0. But here, an important point is that when we access B0, it will evict A0 because they map to the same cache entry, right? Okay. And then we access A1 again. So A1 was brought by when accessing A0 because they map to the same cache block, right? So we sort of prefetch it. But since B0 evicts that block, at this point, we will not have A1 in cache. But if we didn't have this access to B0 here, then in that case, the second access would have been a hit. Okay, and then here the same thing happens. A1 discards B0 and B1 from the cache, and then we get another miss here. And then the same thing happens, and then we again get a miss. So this is what happens in the first iteration. All accesses miss in the cache. And the second outer loop iteration, so as I said, we increment A in each iteration, but we keep accesses to be the same. Okay. And then now, so the last element we accessed was A0, which brought A0 and A1 to the first cache line. So this is a hit, right? And then B0, access to B0 again, this is not in the cache, was evicted, and this discards A1 and A0. So then we access A2, so this is the first time we touch that cache block, so this will be compulsory miss. And then B1 is in the cache because A2 maps to the next entry, right? So A2 will be placed here together with A3. So B0 will remain in the first cache line. So we'll have a hit here. And then since A1 is not in the first cache line, we'll get a miss. Okay. Nice. Okay, I'm gonna now quickly go through some other iterations just to show you the hit and miss pattern that we'll eventually get. So A3, B1, A2. So in this iteration, what will happen is we already have A2 in the cache. Nobody evicted it. This is a hit. Do we have B0? No, because last time we accessed A1, which evicted B0. This is a miss. This is a hit. A3 came together with A2. And then this is a hit because B0 brought the cache line. And then A2 is hit again. Okay, so this is what happens in the third iteration. And I think I'm going to show 2 more iterations. A4, B1, A3. We accessed A3 before. This is a hit. We have still B0 in the cache. So if it's difficult for you to follow what's in the cache, what's not in the cache, you can use this and then basically write it here, what is currently in the cache, and then when you evict something, you can just modify it. But I'm not doing it just because I like to save some time. But in the exam, if you think you can make a mistake, you can do it more safely. Okay, A4 is a new cache block that we'll need to access. So here we'll have a miss, and then for B1 we'll have a hit. And for A3, we will have a hit. So here, at this point, you see that starting with this third iteration, actually, we always get, starting with this iteration, we'll always get hits for elements of B. Because they won't be evicted, we don't access A1 and A0 in those iterations. And we will also get always hit for A3, because we will first access it here in the beginning of the iteration, and then B won't conflict with it. And every second iteration, we will get a miss on this element here. So let me execute one more iteration. So here we will do access to A4, B0, A5, B1, and A4. So what will happen in this case is we already have A4 in the cache, so this will be a hit, this will be a hit, this will be a hit because A5 came with A4, this will be a hit, and this is also a hit. Okay, and in the next iteration, we will basically have hit to A5, hit to B0, miss to A6, it's a new cache line, and then hit again, hit again. Okay, so starting from this, starting from this iteration here, we will have 1 miss and 0 misses, right? And those will interleave. 1 miss, 0 miss. We know that in total we have 16 iterations, so we will end with 1 miss, right, here. And here we have 1 miss for this iteration, 3 misses, and 5 misses. So if we add everything together, it is 8 misses here, 8 misses plus how many? So it's 13 divided by 6, 7, right? So we'll have 7 more misses here. Sorry? 13? That's 7, isn't it? Oh, yeah, okay, sorry. This is 9. Okay. I was like, okay. Yeah, so in total we have 16 miss. And then the rest will be hit. So like it's quite easy to calculate how many accesses we have here in total, right? So it's like 16 multiplied by 5. We have 80 accesses in total. 16 of them will be misses, and the rest is hits, right? We have 64 hits and 16 misses. So based on that, you just do the math. You have the number for, so it takes 5 cycles to serve a request from the cache and 50 cycles otherwise. You do the math, and then you end up with the execution time. Okay? Yeah. Yeah. Yeah, so I think, so I don't remember what we did in the question, but it's not like very explicitly stated what happens exactly, but in the question, so it says, on a miss, the main memory is accessed, and the access fills an 8-byte cache line in 50 cycles. So that will mean you should also apply another 5 cycles to bring the data from the cache to the processor, right? So it should be 55 cycles in total for a miss. So what we used here is so here in the solution, apparently we don't take that into account, so we just use 50. I mean, ideally this should be clearly specified in the exam question, okay? So it will be like all the way to the CPU, you bring the data from the main memory in X cycles, or you bring it only to the cache in X cycles, and then you still have to pay the hit latency. Okay, it will be stated clearly in the exam. Okay, so that was part B. Any other questions? Yes.
I think this is outside the scope of this problem, but for like store instructions, normally we have to consider like the write group loading information to the cache.
Right.
We don't consider that, right? We're just treating it as the same as reading.
Yeah, exactly. Yeah, here it's very simple in this question. Yes. Okay. I had a blank page here to use, but yes.
But here you're assuming that the memory is word addressable.
No, it's byte addressable.
But if you see in the code, for example, if you assume R2 is 1 and R4 is 8,000, the address will be 8,001. Whereas to access B of element 1, it should be 8,004.
Oh, okay.
Okay,
yeah. So here, we also have a mistake in the code, I think. Yeah, I agree with that. So here we should increment with, not by 1, by 4, basically. Yeah. Okay. Okay. Yeah.
Can you just re-explain how you calculate the offset?
Like you're asking about like which elements in the code we access?
Many times in the exercises, I calculate the offset, and I'm not really sure about what I do.
Like this part here?
Yeah.
Okay, so here the overall cache size is 128 bytes, right? So this means we'll have 8 bits to determine like where in the cache data will map, right? So like for example here, we know that a cache block has 8 bytes. So that will mean we will need to use 3 bits to determine the position, the byte position in that cache block, right? So you have 8 different bytes. You address 8 with 3 bits.
So you say that we try to address 1 byte?
Yes.
Okay.
Yeah.
How do you know you're trying to address 1 byte?
So if it's not stated otherwise, you should always assume byte addressable memory. So like in lectures, like everything we do is byte addressable. If it's not byte addressable, it will say that in the question. So it's like I think it's sometimes difficult to think about like things that we have to define in the question. So like we usually end up having such issues. Like you can always find something that people like design differently in their systems, but like I don't know any system that uses anything else than byte addressing, like in the real systems. And this is also what we use mostly in our questions and in the lectures. It's always byte addressable. Yeah. Yeah. I think so, yeah. As long as what you're doing is reasonable, and if there's like any issue or anything not specified in the question, and then you solve it based on your assumptions and everything is reasonable, I think it's good. Okay.
The offset will be always 3, except if we...
So the least So the least significant bits is basically the offset, right? So typically cache lines are 64 bytes. So in that case, you'll have 8 bits that you use. Sorry, not 8. Yeah, you have 6 bits as an offset in that case.
Yeah, sorry.
Yeah. I mean, I don't want to confuse you further, but you can think of it as an address of the byte inside the cache block, right? That's what we call offset. Okay. I will continue with the part C. So here, this part is very similar to the first part, which was very easy, where we had a processor without any caches, and we directly accessed the main memory with 50 cycles. But here, instead, it says that we have a near memory processor, which has only 10 cycle access latency to the data in the main memory. And we don't have caches again. So this is exact same computation that we need, calculation we need to do for part A here, except we change 50 with 10. And then you end up with 800 cycles of execution time. Okay, I think that was very easy. And then part D is, so let me read this quickly. Your friend, oh my God, we have too many mistakes in this question. Your friend now suggests that by changing the cache capacity of the single core processor in part B, she could provide as good performance as a system that utilizes memory processing in memory unit. Is she correct? What is the minimum capacity required for the cache? Blah, blah, blah. So here, she's not correct because no matter how big is the cache, no matter how many entries we have here, we will have conflicts in the cache line 0 here, and then it will increase the execution time a lot, so we can never complete the program in 800 cycles, even if the rest of the accesses are always hit. And we also have compulsory misses. So if you do the math, if you try to calculate the best case here, you will see that you cannot do better than this over here. So basically what will happen is, by just increasing the cache size, you'll only be able to turn those misses here to hits, right? But you will have the rest of the misses here, which are the compulsory misses. Yeah. Mm-hmm.
Does it say that we cannot increase the size of one block? Then we will only have 2 misses, right?
Yeah. So here it is just increasing the cache capacity by increasing the number of entries. You cannot increase the cache size by increasing the cache block. So it has like different consequences, right? As you know, because like increasing the cache block size will also need to potentially increase the number of bytes you fetch from the memory for each request, and then you may also need to maintain some metadata to know like which parts of that big cache block you have brought to the cache. So it changes the design completely. So here, and in this part, you just change the cache by increasing the number of entries you have in the cache. And in the second part here, or in the fifth part, in part E, it asks you how you can change the cache design while keeping the capacity the same, or like also increasing the capacity potentially, how you can change it to improve the performance of the design with cache. And here the answer will be basically, so what was the problem here with the previous cache design? We had those conflict misses, right? So we have to have a design that will avoid the conflict misses. And the best thing you can do here is just to turn this cache to a design where you have two ways, right? In that case, you can keep both B0, B1, and A0 and 1 together in the cache, and you'll avoid all conflict misses. And you don't have to increase the size of the cache. It's not helping because you don't have temporal locality here, right? You only have temporal locality to elements of B and some elements of A. Actually, you have some, but you don't need a very big cache, right? So only like having a cache with like 16 entries, for example, is like good enough. So you don't have to increase that. Okay. Yeah, I think I agree. That's a different thing you can do to improve performance. So basically, in that case, you will not only turn those conflict misses to hits, but also some of the compulsory misses because you will prefetch the data. Yeah. Yeah. So this is like sort of a more open-ended answer, basically. So you have like two options at least. You may also come up with some different change in the design to improve performance. So in such cases, you basically have to list everything that you can think about to improve performance, or yeah. Okay, any other questions? Yeah, okay, I agree with that.
And it was so many times that I'm facing a question and I don't really understand what's here.
Yeah, so as I said, in the final exam, it should be much more clearly defined. Yeah. Okay. Then we will continue.
So this is based on a paper published in 2018 DAC. It's variable refresh latency. So the main observation in this paper was, as we described in the question, is you don't have to wait for the full refresh latency. So what is refresh latency? So, okay. So this is your time axis. I'm just drawing this for one single row. So this is your refresh interval, right? This is just some extra knowledge about this question. And this is your refresh interval. And when you start the refresh operation, it also takes some time. This is refresh latency. And this paper tries to mitigate this refresh latency. And the main observation was that you can actually get a pretty good restoration in the voltage level if you just wait for the 60% of this latency instead of waiting the whole thing. So the remaining questions are going to be based on this observation. So in the first one, the question tells us that here we see a graph on the y-axis, it's maximum number of partial refreshes. So when we just use 60% of refresh latency, it means a partial refresh. And we cannot keep doing this for the whole refreshes. So this plot means, as described on top of that, if I see a value 1 here, then it means that after a full refresh, I can do only one partial refresh, and the second one should be full refresh again. And if it's 3, I do a full refresh, and I can do 3 consecutive partial refresh for the other 3 refresh intervals, and then I need to go back to full refresh again. So this is how this works. And here, what we need to calculate is how much time does it take for a bank to refresh all rows within a refresh interval, right? So here, we only have one single refresh interval, which is 64 milliseconds. And our refresh latency is, the full refresh latency is described as T, and the partial refresh is 0.60, the 60% of that, right? Okay, so what we do here is actually just multiply and add them up. So here, as you can see, like 10%, 60%, 30%, this is the whole distribution of these rows. I can, for the 10% of the rows, I need to fully refresh those every other interval. So it's like interleaves between partial and full refresh. And for 60% of them, I need to fully refresh them after every 3 partial refreshes, right? So what I do here is, this 0.1 comes from 10%, and then half of them should be partial, half of them should be full, right? And for this one, 60%, 0.6, and then 75% of the refreshes should be partial, and 25% should be full refreshes. So I just calculate these, and then add them up, and then it gives me the refresh latency of a bank as this value. So I hope it's pretty clear now. And a lot of people already found this exact number in the exam, so I just assume that it's easy. But if you have questions, you can ask anytime, interrupt me. Okay. So based on this observation, we need to understand like what is our benefit here in this paper. So for that, we need to come up with a good baseline, right? So in our baseline, we see that 90% of the rows can be refreshed at every 128 milliseconds. And 10% of the rows can be refreshed at 64 milliseconds, right? So here what we do is we want to compute the refresh overhead of the baseline where we don't have any partial refreshes. So here I have the value for a single refresh command, which is this, where n is the number of rows in a bank. So refreshing the whole bank is going to take 0.2 milliseconds, right? Okay, so again, I do the same thing that I do in this second part of the first question in the basics. Remember, it was like 60% was being refreshed once in every 128 milliseconds, and the 40% were being refreshed twice. So it's the same story here again. I just look at the every 128 milliseconds, 10% of the rows are refreshed twice, and 90% is refreshed once. So when we just add them up their costs, we see that the bank is occupied for 0.22 milliseconds for every refresh. And this every refresh happens at every 128 milliseconds, so refresh overhead is this number here, okay? So this was our baseline and the answer of this question. And the last part of the question is here. So here we are merging these, like on top of the baseline, we want to add partial refreshes. And in the partial refresh, we have another plot here. So here we have 2 refresh intervals, one for 64 milliseconds, the other one for 128 milliseconds. And the y-axis is the same as before. So here you can see that when we add all these up, it goes to 100%. So this is the distribution. And okay, so let's start with this 128 millisecond ones. So here I refresh all these rows. I mean this 20%, this 65%, and 5% at every 128 milliseconds, right? And for this 20%, it's always full refresh. And for this one, it's one full refresh, one partial refresh. And for this one, it's 3 partial refreshes and 1 full refresh. And then for the 10% of them, I need to refresh them at every 64 milliseconds. And it should be one full refresh, one partial refresh. So just by following the same method, we can see that at every, so you can choose whatever value you want here. I just choose 4 times 128 milliseconds because it makes the calculation much easier. You can go for another value. It's up to you. And you can see that for every 20% of the rows, we refresh this 4 times. And then these 4 refreshes, all of them are full refreshes, and none of them are partial refreshes. And for 10%, I refresh them 8 times because this was 64 milliseconds in refresh interval. And half of them, I mean the four of them full refresh, 4 of them are partial refresh. And you just go like this. And then when you just convert these text to mathematical representations, then you get these equations here. When you just add them up, you can easily reach to at least up to this point. You should be able to reach very easily. It's very straightforward math. And then, yeah, if you compute more, you can get these results. But you can just take this equation and say it X or, I don't know, A, something like that, and then compute the rest of the thing just by using that parameter. And as mentioned earlier, you don't have to compute the final exact value in the exams unless it's explicitly stated in the question. And you need to answer all the questions you see in the text, and you need to show how you get those numbers. We should just see your method, how to retrieve them. Okay, so this was the DRAM refresh question. Do you have any questions?
Yeah, let's start with some new RowHammer problems. Yes, here, yeah, we should have thought about, yeah, what and how we consider when we develop the RowHammer mitigations. Yeah, so the problem, yeah, let's read the problem. So one researcher rigorously investigated the relationship between the DRAM refresh rate and RowHammer introduced errors using real DRAM modules from 3 major memory manufacturers, and yeah, they used the most RowHammer vulnerable modules in each DRAM manufacturer. So yeah, this graph is the worst case scenarios. So yeah, very conservative manner. And as shown in this figure, we can achieve an effectively 0 probability of RowHammer induced errors when we reduce the refresh interval to 8 milliseconds. So here is 16 millisecond, and before we reduce the refresh interval to 8 milliseconds, yeah, the errors of all modules are close to 0. Yeah, so this is because the probability of RowHammer induced error becomes less than that of a random DRAM circuit fault. Okay, and based on this, as a leading computer architect of a company, you are asked to design an efficient RowHammer mitigation technique. Yeah, but your junior engineer suggests a very naive, but an immediate mitigation technique, which reduced the refresh interval from the default value 64 millisecond to 8 millisecond. And this is very straightforward that, the bank utilization and the energy consumption will increase, linearly increase along the number of refresh requests we should perform in a same time interval. So so E and U is linearly increased for number of number of refreshes. And if we reduce the refresh interval, we increase this. So we can easily know the energy consumption and the bank utilization should be increased 8 times, both. Make sense? And the next question is the feasibility of this approach. Fortunately, so the recent DRAM manufacturer successfully released a higher capacity version of the same DRAM module. And you figured out that with the rigorous reverse engineering, they only double the number of rows in a bank and the number of banks in a module without changing any other aspects. So in this case, in this question, asking, how the bank utilization will increase, along these changes, and if the number of banks and number of rows per bank increase 4 times, then how it should be changed. So with just 2x increase, it is still applicable. And so here the current bank utilization is 0.05, 5%. So in our calculation, when it decreased the refresh interval to 8 milliseconds, the bank utilization increased 8 times. And here is some fake information, right? So the bank utilization does not affect it to increase of the number of banks in a module. So we just multiply 2, which means double the number of rows in a bank. And this is 80%. And so this is possible. So in terms of RowHammer protection, because we can refresh every rows within every 8 milliseconds, so we can protect against the RowHammer attacks. But it is quite impractical because the most of bank utilization is consumed to the refresh. And the number, if the number of rows and number of banks increases 4x, and it is impossible to protect. Actually, it is impossible to reduce the refresh interval to 8 milliseconds because bank utilization becomes larger than 1. It means that even though we spend all the time for refreshes, we cannot refresh every rows in a module. And it means we cannot apply this approach if the number of rows and number of banks and number of rows increase to 4x. Okay, so this approach, this reducing refresh interval is not feasible when DRAM scales out. So yeah, we should think about another approach. So due to significant overhead of reducing the refresh interval, you can decide to find another RowHammer mitigation technique with lower overhead. So the junior engineer proposed another technique which is counter-based. So in this approach, the memory controller maintains a counter for each row R, which increments when an adjacent row is activated. So yeah, note that there can be some multiple approaches using counter to mitigate the RowHammer effect. For example, we can count the number of activation of a row, and if it exceeds the threshold value, we can activate the adjacent rows of the activated row, right? But here, they did not choose that approach, but instead they count the adjacent rows activation, and if it exceeds the threshold value, it refresh the victim row, potential victim row. So there are many pros and cons for each approaches. Okay. So the question is, so here are a bunch of information about your DRAM modules for now. So here is interface generation and cost latency and TRCD, a bunch of information. And the question is asking, are the given specification enough to implement the proposed approach? And I think it is quite open question, but this question is asking the essential information to implement this techniques. So what I intended is we should know if we do something with about adjacent row, we should know where is the adjacent rows, right? But as we covered in our classes, a DRAM manufacturer does not open it. It is normally confidential. So we should know the existing mapping between row addresses and physical rows. In this case, Anyway, suppose that all the necessary specification means the exact mapping between the row address and physical rows for implementing the proposed approaches are known, and calculate the maximum value of T. So the threshold value that can guarantee the same level of security against the RowHammer attacks over when adopting 8 millisecond refresh intervals. The reducing the refresh interval means that it limits the number of activation within the consecutive refresh, right? So the maximum we can, if we reduce the refresh interval, we can limit the number of activations, number of hammering, because the activation, the hammering method is now activation. We can limit the maximum number of activations. So so actually, to calculate this very optimally, we should know. We better to know the possible number of possible activations within 8 milliseconds. But in theory, we can the maximum bound of the number of activations in 8 milliseconds with this low cycle latency, which is the sum of TRAS plus TRP. And so it means total, about 65,000 activations can be possible in single 8 milliseconds. So if we set the threshold value as this value, then we can at least guarantee the same level of security against the RowHammer attack over with the 8 millisecond refresh intervals. Make sense? And so the next question is asking the number of bits required for maintaining counters in each memory controller, and it's very easy actually. With B, let B is the number of bits. We can maintain these many informations, and so it should be larger than T, and definitely we need to calculate the maximum value. So minimum value of this. And we can simply know with this some logarithm method, and this T is 18. So so for more correct more correct equation inequality is this. And with this value, we can simply calculate the number of bits required for the counters. And it can be increased 36 millibits if the number of rows and number of banks are doubled. Okay. So the reason why we use the maximum threshold value is to minimize the performance over it. So this question asking the goal of that we use the maximum value of maximum threshold value. So we can reduce the size of counter in each memory controller if we use a smaller value T. For example, if we use just a threshold value as 1, then the size of counters definitely should be increased a lot, but we need to refresh adjacent row whenever we activate our row. Twice or something. So the performance and energy overhead from unnecessary activation or refreshes is the cost of using a smaller threshold values. And the final question, you recall para, which is proposed in the first RowHammer paper. And here is some description of how para works. And I suppose you are already aware of it. So the key question is, we know the error for para. So error rate of para experiencing sorry for that. We know the probability for para to experience an error in 16.4 millisecond, which is very small. And let this as what? P64 millisecond. When the parameter, the probability parameter in para technique is just 0.001. And this is the worst operating condition. And the question is asking, how can we how we can estimate the probability of experiencing an error in 1 year based on this value. So yeah, so the problem, so this is the probability of experiencing an error for 64 milliseconds, and the question is to get this, which is the probability of experiencing an error for para in a year. Then we can consider a year as a sequence of independent 64 millisecond time intervals, and the number of 64 millisecond time intervals like this. Let's say this is this is M, and we can the number of errors in a year can be modeled as a random variable which follows a binomial distribution. With the parameters n. N is the number of 64 milliseconds time interval, and the probability is this value. And therefore, if the probability that at least one error occurs in a year can be calculated, the variable x, the probability of that variable x is equal or larger than 1, larger than or equal to 1. And this is because x is discrete value, we can simply know is like this. And in binomial distribution, the probability of the event never occurs is simply just multiply n times, and the final answer should be like this. And this can be, fortunately, this can be calculated with the calculator in your PC maybe. So, but it should be fine. Just leave this form in exam or homework as well. But and definitely if you use some approximation or some inequality, for example, Markov inequality, because this variable x should be this variable x, and the probability should be larger than positive value. Then we can use Markov inequality to bound the maximum value, or and this binomial distribution with very large trials and very small probability, then we can approximate the distribution to Poisson distributions. So if you use that and refer to that reasoning, then it should not a problem in this question. You will get all the credit. Okay, any questions?
The next question.
So this is a very interesting question, hopefully. And it's related to the lecture number 5 about accelerating genome analysis. And in this question, you are asked to solve 3 parts about finding the edit distance between 2 strings. So how many of you still remember this lecture? Okay, very good. All right, so edit distance is the minimum number of edit operations that you need to do so that one of the sequences will be similar to the other one. So those edit operations are 3 types, can be substitution, deletion, or insertion. And basically, you could follow the dynamic programming algorithm where you design it yourself, or you solve it, you calculate it for each of those 2 sequences, or you could, if you are smart enough, trying to find the number of operations that you need to do so that one of those 2 sequences will be similar or exactly typical to the next one. So let's see this example. You have one tag, and on a stack. Is that correct? Okay. So apparently, you have the tag part is common between the two sequences. So that gives you 3 matches. And you have another seven characters that don't exactly match. So you have the S, R, and so on. So anyway, so for those kind of questions, you need to start from the first character, very first character, and you move all the way until the end, okay? So if you try to do this way, that will give you some incorrect answer. And you need to note that, though you might find a way that you could make this sequence similar to the other one, but might not be the minimum, and that will lead to a wrong answer, okay? So you have to be very careful about those. And that's why we use dynamic programming algorithm to solve such kind of questions, so that we can enumerate all kind of prefixes. Oops, it's too late. Okay, can everyone see it? Okay. Okay, so in dynamic programming algorithms, we're trying to enumerate all prefixes and see which one gives you the minimum number of edit operations. So how we do it, let's try again. So you have the, let's type it again, one tag. And let's start with the D. Does D match here? No. Does it match the next few characters? No. So probably this should be a substitution, okay? Now this is one operation. Now we have the O. Does O match the corresponding next character in the second sequence? Yes. Okay, that's perfect. So we have an exact match here. And then we move to the N, which is exact match. And then, unfortunately, we have another N. Does it match? No. Does it match with the previous character? Yes. So apparently you have an alternative solution here where you could have an exact match here, right? So you could delete this N or the next N, right? Both of them correct, by the way. So you could do that. And now what's the next? It's E. Does E match the corresponding one, which is A? No. Does it match with the next one or the previous one or the few previous? No. Now, how few you should go? How far you should go? Probably if the two sequences are short, then you shouldn't move more than 2 or 3 steps around that. But sometimes we call it a banded edit distance, where we restrict the number of steps you could move forward or backward. And in this banded, we give you a threshold, 2 or 3. So that will restrict you moving how many steps right or left. Anyway, so and apparently here we have another deletion. By the way, if it is a deleted character from this sequence, it's same as if you insert it in the other sequence. So deletion or insertion, same answer, okay? Now what's next? So we have the R, same story. We need to delete it. And we have the S, and then we have the tag. So how many edit operations we did here? We did 5 steps, 5 deletions from here. We have the 1, 2, and we have another 3 here. Or you could do 5 insertions to the other sequence. Okay? Any question? Yes? So if you are banded with some limited number of edits, yeah, then probably this exceeds the threshold that we set in advance, then probably you don't need to continue. Because anyway, what does mean banded is you have the dynamic programming table, right? You have some diagonals. So banded mean number of diagonals that are next to the main diagonal. So if you have the main diagonal, which is the one in the middle, now the banded mean if it is 3, then you are allowed to construct only 3 diagonals next to the main diagonal. Likewise, you can construct another 3 here. So probably if you have 5 edits, for example, then your computation need to be exceed this limit, which is the band you have, which is 3 and 3, plus the main diagonal, 7 diagonals you have. So you cannot compute it using this dynamic programming table if it is banded. Okay? So probably you need to stop computing after you exceed that threshold. Then you can say that those 2 sequences has an edit distance more than the threshold, which is 3 or 4. Okay? So now let's go to the second. So let's try with the S. S doesn't match, apparently. Does it match with the next? No. Next, no. So apparently we need to delete this character from here. Then we have the A, same story, no. Then we have the M. We need to delete it. So we don't need to delete it, actually, here. Maybe substitute it. It's more accurate. Why is that? Because we want to keep it the same length. Okay? So we have the S and then the tag. So if we substitute the S with the I, M with the E, A with the R, and S with the F, then it will be exactly match, right? So how many edit operations did we do here? So we said 4, right? Because we need to substitute these. Okay. Now, we need to have this compared with a null sequence of empty characters. So apparently either you add all of these characters to the second sequence or you deleted them from the other one. So how many operations do we need? Equal to the number of characters here. Okay? All right. Now, why we explain the lecture about edit distance or other metrics that we measure the similarity or the difference between 2 strings? So we need that in genome analysis, for example, to tell us how many differences between your genome and the other genome, which could be a reference or somebody else in your family, for example. So here's an example of how we do that. You are given those 5 reads, and at each read, we chop it into 3 k-mers. And for simplicity, I give you the delimiter here, which is underscore, that divide the k-mers of a single read. So k-mer, the k here is the length of this substring or subsequence. So here we have the k-mer length is 5, so k is 5. So how many k-mers we have per read? 3. So we said in the question that this is a hash-based read mapper. What does that mean? Meaning that the first step in read mapping or in genome analysis, the indexing part will be based on a hash table. Okay? This is what does mean hash-based read mapper. That's why you are given this hash table, and you are given a bunch of reads. You need to map those to the hash table and start extracting some locations from the reference genome. So we are going to use the very basic method of doing that without any filtering, without any advanced mechanism in the first part of the question, which is this. Can you see it? Okay. So here you are asked that how many times you are going to apply this edit distance function. So how we do that basically is picking the first k-mer from the first read and go to the hash table. Does that k-mer exist in the hash table? If yes, then we extract all the corresponding locations. And at each location, we apply or we perform the edit distance function. So we pick the first k-mer, which is A's, 5 A's, which is here. How many locations? We have 6 locations. So at each location, we are going to check one by one the edit distance between this read and the reference genome at this location. So starting from 10 all the way to the same length of this, which is 15. So we start from 10 to the position 35 or 25, sorry. And we do the same thing with the other locations. Okay? So we pick from the reference at this location and we compare it with the read for edit distance. Okay, so how many times we do that? So the first one here, how many times occurred? So 6 plus AACs, which is here 3 times, plus the 5Gs 3 times, and now the second read, 4 A's plus T, which is 2 times, and then double G, double C, T, which is 5 times, plus A's, again 6 times. Now the third one, AETs. So I'm going to do some cheating here and copy the answer because it's repeating itself, right? Do you want me to continue? You just need to count how many times you get the location basically for this. So let's have it here, 2 plus 0 plus 0, and then 3 plus 2 plus 5, and then 6 plus 5 plus 3, and that will give you 51. Locations need to be examined for edit distance. Okay? Yeah.
I just wanted to say that when I did it, because you can call edit distance with not the same size of the string you put as input.
Uh-huh.
So I chose to put 5 characters as input and to only call the edit distance on the ones that you didn't know that they matched. So for each read, you only call edit distance twice, but with parameter of size 5.
Oh, wow. Okay. Why would you do that?
Because it was not specified. And it actually, it's quicker.
Okay. So basically, you already know from the hash table that the camera is exactly matched, right? So now the question, where to perform the edit distance. So you already know that those 5 characters exactly matching with the reference, right? Now, whether you go to the next few characters or the previous characters in relationship with this Kamer, right? Now, okay. Yeah, if you assume so, nobody can argue with you, right? Unless it's specified in the question. But that's interesting. Okay. So now the second part, trying to do some sort of smart way of doing the comparison between the strings. So they ask you to use adjacency filtering. Adjacency filtering means you need to relate the Kamers together coming from one read. So you don't need to perform a distance per each Kamer. So meaning that here the distance between, so to call a Kamer adjacent to the next one, the distance between 2 Kamers should be 0. This is how they define it here. You can see they said if the first Kamer happening at the location X, then the second one should be at X plus K, which is 5. So they should really be next to each other. The distance between the Kamers should be 0. Okay?
Why would you call edit distance if you know it's 0?
Yeah, you can consider it as Hamming distance, for example, or edit distance 0.
So why do you call it if you know that it's...
So this is just to simplify the question so that you don't need to calculate the distance and subtract the... For example, if we allow for 5 steps between 2 Kamers, then that's considering 0, 1, 2, 3, 4, and 5. So you need to deduct all those possible values from a location such that you're on safe side, right? So this will complicate the calculation for your side, right? So anyway, if you want to assume that there's a single step between the Kamers, here the assumption is not valid, right? Because it's already given the question that the step is 0. So you cannot assume something else. The distance between the 2 Kamers should be 0. But the answer is not 0. Let's see what the answer is. Okay, so how we solve this question? Again, exactly same way, but we need to relate the 2 Kamers together, or the 3 Kamers coming from the same read. How we do that? Let's go to the first read, first Kamer. Then the 5 A's. How many times happening here? 6 times. Okay, now we shouldn't stop and perform at the distance. We need to proceed to the second Kamer, which is 4 A's and C. How many times happening? 3 times. Okay, now which one of these locations is adjacent to these 6 locations? How we do that? Now the 15 is really next to the 10. Why is that? Because the k-mer size is 5. If the k-mer length is 4, then the distance between the two k-mers is 1, right? So meaning that this location is adjacent to the 10. Now 610 is not adjacent to any of those, right?
We don't see on the...
Oops. Okay. Yeah, thank you. So the 15 is adjacent to 10, right? You agree on that. And the 610 is not adjacent to any of these. Why is that? If you add 5 to any of those, won't give you any of these locations. So the same thing for 720 is apart from 710 by 10 steps. So this is not valid based on the definition given the question. Okay? So none of these valid. Now we are having only single location coming from this. Now it's based on the third k-mer. If it exists adjacent to these two, or at least to this AAC, then we are going to perform at a distance here. Yeah, I know it's stupid to perform at a distance here. Why is that? Because it's already exactly matching the 3 k-mers. So now let's see the 5Gs here. The 20. Is 20 next to 15? Yes, given that the k-mer length is 5. So we are going to perform at a distance here once for this read. How about the others? 600, 700, they are not adjacent to 15. So we just ignore them. Now we do exactly the same thing. Let's repeat for the second read, for example. So we have the 4 A's and single T, which is here, and we have 2 locations, okay? Now let's go to the second one. 2 G's, 2 C's, this one. Now let's start from the first one. Is 55 adjacent to 50? Yes. And 620 is adjacent to 50? We should check the entire list, okay? We cannot ignore one of them, even if we check it before. This is very important. So the 620 is adjacent to 15? No. Is it adjacent to 615? Yes. So we have 2 locations now. Now we repeat the same thing for those, and luckily they are not adjacent. Okay. Should I repeat it? Okay. All right. So now the third came from the second read, which is 5 A's. Now we said we have 2 adjacent k-mers at this location, but those are not adjacent. So we need to check one by one for all of them. 55 adjacent here. No, maybe here. No, this is backward. You could apply it if you want, if you assume so, like not considering always the forward path. You could follow the backward, right? And actually, we do it in real life. Why is that? Because we have the DNA strand, and we put it in the machine. The machine starts reading character by character, right? But we don't know whether we are reading from the first character or the last character, right? So we always do the mapping backward, forward, or forward, backward, okay? So if you assume so, it's okay. If you don't assume it, it's correct again. Because based on the definition, it should be in the forward direction. We always have the plus sign, okay? Okay, so we are comparing now 55 with this. No, it's too far, too far, too far. So this one, no, we should ignore it. Now 620 is, oops, sorry. So this is the third k-mer, right? And this is the second. So this should be an increment of this, right? Yeah. So this is correct. Yeah, it's good that we mention it because to know that there's a forward and backward direction. So anyway, this 60 is next to 55, so it's correct. So we should keep this potential mapping, let's call it. And now 620, we should look for 625 here, which is this one. So we have it there. So this is a correct match. Now here, 650. What's next should be 655. Do we have it here? No. Okay. Yeah, anyway, we shouldn't continue, right? Because they were not matched from the second k-mer. So we have only those 2 positions, which is The first one was here, right? So we have 50 and 615, and from the second Kamer, 55, 620, and from here we have 60 and 6025. So we have two mappings for the second read. Now you can repeat this exactly the same steps. Do you want me to continue? How many of you want me to continue? Okay, good. So we have 2, here we have 0, I guess. Here we have 1 and 1. So in total we have 5. 5 times we need to perform edit distance. So apparently this smart way of using adjacency filter, reducing the number of times need to perform edit distance, which is very expensive because quadratic time, from 51 times only to 5 times. So you can see a huge reduction in the execution time of this software. Yes. What do you mean comparing?
Since now we are applying edit distance to 15 characters instead of 5.
No, the edit distance here between 15 character, right? So the read length is 15, right? So this location of the Kamers, which is starting from 50 to here, 60 plus 5, which is the end of the Kamer. This is the start index of the Kamer. So you need to add 5. So again, this is 15. So the length of this, the length of this is 15 again, right? Similar to the length of the read. So you have from 50 to 65, this portion in the reference. The reference is 3 billion character, around that, 3.2. Okay? So we only go to the location 50 all the way to 65. And then we pick this string, we go to the read, and we compare them together. Now they are equal length. Okay, so now let's use another method. Yes?
I just still don't understand why you perform this 5 edit distance. You know that the distance is 0, right?
Yes, that's true. Okay. That's a good question. But again, we mentioned that the distance between the cameras is considered 0 for simplicity of the calculation, right? But if I consider it to be 1, for example, then you don't know whether this 1 is insertion, deletion, or substitution, unless you try edit distance algorithm. This is in case I allow for a distance between 2 Kamers to be 1, for example. But here, in this question, I ask you to keep the distance between the Kamers as 0. Okay? But that's true. Maybe we should try it. Let's have this question in the exam. Let's try the distance between the Kamers to be, for example, 5. Let's see. Okay? Yeah, that's a good point. So again, if you are not sure about any point in the exam, you need to assume it. Otherwise, you won't solve the question. Okay? But if the question asks you for something very strict, you cannot assume in this case. Right? Okay. Yeah, some people were like writing half page of assumption, which is invalid. That's not true. Yeah, you cannot just write whatever you have in your mind. It should be valid, should be logical, should be following the given points in the question. Okay? Yeah, we still have the third question, which is some smart people like you proposing another method, which called cheap Kamer selection. So now let's try and see whether that improved the execution time or the number of times we are executing this edit distance function or not. So let's go back to the read. So we have the read set, and the definition of cheap Kamer. Luckily, you got all those definitions, so you don't need to memorize them, right? So we defined already this method, and whatever new algorithm we propose in the exam will be defined. Okay, just you need to follow the definition. So it says you have a threshold, and whenever you have many locations, more than the threshold, you just ignore this Kamer, or you don't perform it at distance. Okay, as easy as this. And what's the threshold here? The threshold is set to be The threshold is set to be 4 here. And so now the question, do we need to apply this cheap K-mer selection on the solution we perform in B or A? Why? Do we mention something about it? Okay, it seems we didn't mention about it. So again, you can assume it here. So you can assume that I'm going to follow the adjacency filtering and applying the threshold together. That's true, it should be correct. Or I'm going to change step 3 here and apply the threshold, where here doesn't mean I have adjacency filtering, okay, which is here, the original question. Okay, so both of them is correct. So now we go here, we pick the first K-mer, here, and we go to the hash table, 5 A's, we got 6 locations, 6 hits. Now my threshold is 4, so anything exceeding 4, not equal or greater, but exceeding 4, we are going to ignore it. So we ignore those 6. We could say that we will consider only 4 locations without ignoring the seed, meaning that I'm going to consider those 4 locations and ignoring those 2, for example. If you assume so, it's correct. Okay? Now we go to the second K-mer. It's less than 4, so we apply here for each location an edit distance algorithm. So you have 3 times and 0 time from the previous, if you assume so. And then you have 5 G's, which give you 3 locations, so you need to apply here 3 times edit distance. Now this is for the first read. You could do the same thing. Let's take, for example, the last one. So you have 5 A's, 6, the same thing applies here. It's up to you. You want to consider 6 location, or you want to consider no location, or 4 of them only. But you cannot consider 6 because the threshold is 4. So the second K-mer is 2 G's, 2 C's, 1 T. You got 5 locations. Same thing you could do to the 5 A's, where the threshold is 4, so you can consider the first 4 locations, or you ignore this one. And then the last K-mer here, it's 4 A's, 1 C. 4 A's here, so you got 3 locations. Sorry, on safe side, you can apply edit distance to 3 of them. Yes? Yes. Violating the question. Yes, that's true. That's true. Then our assumption is not valid. Okay, so you cannot, if there's 6 locations, you cannot consider 4 of them and ignore the rest of them. Okay, so if it is exceeding, just ignore it. As simple as this. Okay. So yeah, you can assume whenever it makes sense for you to solve it, but you have to be careful about what the question asks you to solve.